This is the 15th in a sequence of many videos about parametric curves. We are focused on developing calculus tools to understand them and the motions that they model, and we are approaching the subject from a physical, intuitive, graphical perspective. We're not developing the calculus in a rigorous way. In the previous few videos, we've been focusing on using Mathematica to illustrate an important fact related to physics and calculus, that the outputs of the speed function give you the slopes of the distance traveled function. What do I mean by that? Imagine moving in a car or walking or running. You start at a certain time, call it time 0, and you travel a certain amount of time, call it time t. The distance traveled function, which I've called dist of t, tells you how far you've gone during that amount of time from time 0 to time t. And the speed function, speed of t, tells you your speed at the moment of time t. If you were driving a car, it would be what your speedometer is showing at that moment in time. And again, the outputs of the speed function, the value speed of t for different t's, give you the slopes of the distance traveled function at that same value of t. That's the main thing we're trying to illustrate in all this. So we've got Mathematica code down here that I showed you in the last video to emphasize this. Before I get back into the code, I want to make a little change here. First of all, I want to highlight this in red, this fact here, this fundamental fact that the equation of the tangent line to the distance traveled graph at an arbitrary moment in time, t equals b, is given by this equation. I also want to change the name of the dependent variable so that we don't get it confused with the second coordinate for the motion. It's not the same as the second coordinate here. This is going to be some other dependent variable. I might call it distance. Okay, so we are looking at this equation of a line. The distance is a linear function of t. This is not the distance function itself. It's the tangent line to the distance function, dist of t, at a certain moment in time. This is really a slope, a point slope form of the equation of a line. Speed of b is the slope of that line and of the curve at that moment in time b. I got to multiply that by t minus b and then add the second coordinate of the point that I'm thinking about, which is the output of the distance function at time b. Spend some time thinking about that if that was confusing. So then I have this code that I can enter, and we have this example we were thinking about. To illustrate this main concept, the motion is in the upper left corner. It's in this particular motion, you see it's starting out fast, then it slows down and in fact stops for one moment in time, and then it speeds up again because this h of t function has that kind of increasing very rapidly, then very slowly, then rapidly again kind of behavior to it. Its slope is high to begin with, then its slope is 0 in fact at t equals 1/2, and then the slope becomes high again as t approaches 1. And that's why this kind of motion is happening. The graph down here in the lower right is very important for us here. This is what we use to illustrate the concept that I was just talking about. The distance traveled graph is in blue. We're traveling 5 units of distance here total. The speed graph is in red. It is giving you the slope of the distance traveled at each moment in time. The magenta colored line that you're seeing move here as time goes by is the tangent line to the blue graph at different values of time. Its slope is given by the values of the red graph. I want to emphasize that now by making a few changes to this. I think I'd like to add another point with my list plot here. The point b comma speed of b I'd like to add to this. I'd also like to make these points bigger, maybe 0.04 instead of 0.02, so we can see them better down here. Yes, now you can see those points better. You see the same point we saw before, this point where we're drawing the tangent line on the blue graph, and we see a corresponding point at the same value of b on the red graph. The second coordinate of that point on the red graph is giving you the slope of the tangent line, the magenta line on the blue graph. That's the main point here. Let me also add a little bit more. We've seen the use of graphics before. I will use graphics again to let's make it a thick thick red dashed, you can add this option dashed in here, line. This line is going to go between 2 points. Just typing in the syntax here. The first point is going to be the point 0, comma, speed of b. It's going to be on the vertical axis in that lower right graph. And the second point is going to be the point b, comma, speed of b. Think about what you think that's going to do. Take the time to do that. Now we'll look at it. I've tried to do that. I did that because I want to emphasize that it's the second coordinate of that point on the red graph that is giving us the slope of the corresponding point on the blue graph. All right, let's confirm this numerically and visually as well. Here at time equals 0.2, so b is 0.2, I've frozen it here. What again I claim is that the slope of this magenta line is the same as the value of the second coordinate of this point on the red graph here, the height of this dashed red line. Is that true? It looks like the height of the dashed red line above the horizontal axis is at about 5. Is the slope of this magenta line 5? Let's think of it in terms of rise over run. This point over here looks like it's at about the point 1, comma, well, it should be maybe 5.5 or something. And this point down here is at the point 0.2, comma, about 2 or so. Rise over run, 5.5 minus 2 or so divided by 1 minus 0.2 is an approximation. Okay, this is an approximation to the rise over run for the magenta line. This should be around 5. Not exactly. Okay, 4.375. I'm trying to visually estimate where these points are. If this was a 5 instead of a 5.5, then that's further off. Okay, so it seems like it's reasonable, at least. That's what I'm trying to do is illustrate the reasonableness of this. We could try to verify more precisely what these things are. The true speed at time 0.2 is actually 5.4, so that seems kind of further off than I was guessing. Maybe this number is closer to 0.1. Maybe this number is closer to 1.5 or something. That's getting closer at least, okay? So that's just a visual numerical approximation to our main concept. To end this video, let's just show you one more example. Since this example is an example where we start fast, slow down, then speed up again, let's do an example that's the opposite. Start slow, speed up, then slow down again. And I want you to think about this on your own. I'm going to use the function 0.5 minus 0.5 cosine of pi times t as an example of an h of t that will generate motion that starts slow, speeds up, then slows down again. I would very much encourage you to think about why that's happening, but let's just verify that it's happening. Yes, this motion starts out slow, speeds up, then it slows down again. You can see the graph down here illustrating that too. The red graph is the speed graph. Starts off slow, low value, gets higher speed up to close to 8 meters a second, then back down slow again, back down to 0 when time is 1. And you can see that in the motion. Starts out fast, or starts out slow, speeds up, then starts out slow again. And you could also see why it's evident in the x and y graphs in the upper right and lower left. And I'll end the video there.